Hello and welcome to this session on algorithms where we'll look at Quicksort algorithm. We'll look at the intuition behind the algorithm as to what is the basic idea. We'll look at some examples and also the implementation. This is going to be iterative in the sense that I'll jump back and forth between the example and the code so that the understanding is better. Let us consider this set of numbers. The idea behind Quicksort is very simple. Take a number, in this case let's consider 18, and find its right position. That's as basic as that. We'll build on that. So 18, we have 7, 8, 13, 12, 9, 2, 5, 14 and 6. All are actually smaller than 18. So 18's right position is actually right at the end. And we swap 6 with it. So this is bringing it into the right position. And now what we have done is we have created two partitions. Left partition, the right partition. Right partition has no numbers because 18 is the biggest number. Left partition has this set of numbers. And now we again start with the first number over here, 6, and try to find the right position for 6. We do this iteratively, actually recursively, and then we end up with all the elements in the right positions, and that's how the list is sorted. We had considered a very special case, actually a corner case, where 18 happened to be the biggest element, so it went to the extreme right. So let us go one step further and let's try to put 6 in its right position for this partition so that we get a grasp of what is the basic idea. So here we look at all the elements which are less than 6 and put them on the left side of 6. 7, 8, 13 can be passed, 12 can be passed, 9 can be passed. 2 is smaller than 6, so 2 comes here. 5 is smaller than 6, so 5 comes here. 14 and 18 do not, actually 18 we should not even consider because 18 is in its right position. So we put 6 here, 7, 8, 13, 12, 9, 14 and 18. And now 18 and 6 both are in their correct positions, and 6 has further divided it into two partitions that we see on the screen. If I were to show you the algorithm, the actual algorithm or the actual implementation of the algorithm, then this intermediate stage would never occur. I have been deliberately inaccurate in some of the descriptions here. The intent being that we should first understand the intuition behind this quicksort algorithm. Once you understood the idea, the main idea behind the algorithm, then it becomes very easy for us to look at the algorithm and the accurate implementation of it. So let's just play along for some time. So let's get a bit more formal now. We started with the number 18. We call this number the pivot number. We could have chosen any number to be the pivot. We could have chosen 12 or 6, but we'll stick to the first number in the array as the pivot element. Now our job is to put 18 in its right position. And how do we do that? We actually start with two markers. Let's call them I and J. And for I, we start moving towards the right, iterating over the elements, looking for the condition that if any element is greater than the pivot value, 18 in this case, we stop. And then from J, we move towards the left, looking for condition that any element which is less than the pivot value, and we stop. Now, if I has not crossed over J, then we swap the values. Here, we do not interchange the values of I and J, we interchange the values of array elements at ith position and jth position. Once the values are swapped, we increment I and we decrement J, and then we proceed again and repeat the same process. So let us play it out for one example. Eighteen is a pivot element, so we have to compare against it. We start with 7. Is 7 greater than 18? No, it is not. 8, it is not. 13, it is not. 12, it is not. 9 is not. Actually, 18 is the biggest element in this entire array, so we'll end up having I go till 6th. But J is also pointing to 6. And so what will happen is that the entire thing will terminate without any matching condition. And at the end, we swap 18 and 6. This is the step that I did not mention here, but we need to do that. At the end, we swap the pivot element with its element that is at the right position for 18. So 6 comes here, 7, 8, 13, 12, 9, 2, 5, 14 and 18. Now 18th is in the right position now. What it has done is, it has created two partitions, right? Right partition has no elements because 18th is the biggest element. Left partition has got 6 to 14. And now we need to start with this smaller partition, and 6 becomes the pivot element. 7 becomes the ith element and 14 becomes the jth element. We start going this way again. Is 7 bigger than 6? Yes, it is. So we have to stop. Then we look at j value. Is 14 lesser than 6? No, it is not. So we proceed. Is 5 lesser than 6? Yes, it is. So we need to stop. And we interchange these two values. So 5 comes here, 7 comes here, 14 stays where it is, and 18 is untouched because 18 is already in its right position. And then I points to 8 and j points to 2. Is 8 greater than the pivot value? Yes, it is. So we again stop here. Is 2 lesser than this pivot value? It is. So we again stop here and we have to interchange again. So 2 comes here and 8 comes here. Then I points to 13 and j points to 9. Is 13 greater than 6? It is. So we have to stop again. Is 9 smaller than 6? It is not. So we go further. Is 12 lesser than 6? It is not. So we go further down. How about 13? Oh, here I is, and in this position I is less than j. So they have crossed each other. So we cannot do anything more. So we write 13, we write 12 and 9 over here. And we have the pivot element 6. That 6 needs to get interchanged with 2. Okay. 2, 5, 6, 13, 12, 9, 8, 7 and 14 and 18. Out of these, 18 and 6 are now in their correct positions. And 6 has created two partitions, 2 and 5 and 13 through 14. And these need to be taken care of. Now let us look at the building block of the code, and we'll jump back and forth between the example and the code so that we can understand it much better. So here I define a function Quicksort which takes an array to be sorted. By the way, I'm writing this program in Python, so if any one of you is not familiar with Python, I would just recommend to tag along. It's very simple to understand. It's almost English-like, so do not worry about the syntax. Just follow it. Here I call Quicksort, and what I do immediately is I say sort, and I say array low and high. Now you might be wondering what is low and high, where are they coming from, and why am I calling sort immediately after calling Quicksort with the array. The thing is, if you observe in this example, when we picked up 18 as a pivot element and put it in the right place, then it divided this entire array into two partitions, 6 to 14 and beyond 18. And likewise, when we further went along and created 6 as a pivot element, then it created two partitions, 2 and 5 and 13 to 14. So low and high essentially are the positions which point to the start and the end of the partition. So in this case, 6 and 14 are the lows and the highs of the partition which is left to the 18. For this case, we have 2 as the low element and 5 as the high element, and again 13 as the low element and 14 as the high element for the left side partition, right side partition. And how do we get this initial values though? So initially the entire array is unsorted, and our low and high are going to be the first element and the last element, obviously. So low is equal to 0 and high is equal to len of array minus 1, right? Now I need to define sort function, and sort is taking array low and high. Okay, now we are at the meat of the function. What do? We say choose a pivot. Remember, we have to choose a pivot, and then once you have chosen the pivot, iterate over the 2 partitions, right? After having put the pivot in the right position, right? That is what we are supposed to do. So we chose 18 here. 18 has to go to its right place, in this case in the last position. How do we do that? So for that, forget for now how this pivot is chosen. In this case we will choose the first element, but what is more important is we have to put the pivot in the right position. But is that the part of sorting algorithm? Not really. Sorting should not be doing that. That's a different thing altogether. Iterate over the 2 partitions is what sort is doing. So what it says, what it should do here is sort array and then low, and then we go to the pivot position minus 1. So we sort, we are assuming that something magical has happened before this sorting, and once 18 has been put in the place, then from 6, which is the lowest element, till 18 minus 1th position, which is 14, we need to sort this array. And likewise we need to sort this one on the right side. In this case again there is no right here, but we have to do it. So sort array pivot correct pose plus 1. This is the low, and what is the high here? The high is high, right? We have got the high anyway. So this will just get the position, but the question remains. How and where did we get the pivot correct pose from? Isn't it? So we say, okay, go over here and we call a function which says we call the pivot correct position, we call a function called get correct position, and it again goes through the same high array with low and the high. We need to provide that. Okay, good enough. So we define that function now. This might be referred to as partitioning scheme. If you look at some of the text, it might be defined as partition. The idea is the same, except I just want to be more comprehensible with the choice of names. For the first time, remember, I mean, whenever we are coming, we are choosing the first element as the pivot element, right? So that choice is very simple. Pivot lm is equal to air of flow. And then you might want to ask, if it is just as simple as that, simple as choosing the lowest, the first element as the pivot, why did we not do it in the previous function? And it's a very valid question, except we have to remember that we just do not have to choose the pivot, but we also have to run this algo that we saw. Remember this entire algo that we had, where it is, if you see here, this entire thing. So we had this entire thing which needs to be implemented after we have chosen the pivot. So we have to do that now. So we had created markers. It's a bad practice to call them I and J, but I'm just gonna stick to it for simplicity's sake. So bear with me here. So we choose I as the element, as the marker is the first element after the pivot element, right, to start with. And what is the higher element? It is the J marker is the high element. Now what we say is, while I is less than equal to J. This is our base condition, that till the time that I is less than J, that less than equal to J, that means they have not crossed over each other. What you have to do is, we said the conditions are, we are looking on the left side, the condition should not be greater than the pivot element. That is what we are looking for. So iterating marker is I, while array of I is less than equal to pivot element. Okay, pivot element was array of low. We had initialized this, in this case 18. While it is less than that, and I just used C's syntax for and I is less than J. We have to do this. We have to keep this condition here, despite being under the condition I is less than equal to J. This is very important to understand, because so once we have solved here, right? Once we have solved, we go further and we keep on repeating this process, and that is what this while loop takes care of. This particular I is less than J is a condition for the inners, for just before the swaps, and we say I, we increment I, isn't it? Till it is less than the pivot element value, and till I is less than J, we keep on incrementing I. And you have to bear with me because this variator is a bit funny. So now the second one says that array of J, we are now moving from right to left, array of J till it is greater than equal to pivot element. We should go further, and again J is greater than equal to I. I could have just mentioned I is less than J, but I just want to specify it in terms of J because we are in the second loop, right? And here we have to decrement J. So just to reiterate, what we are doing here is, in this particular piece of code, when we are traversing from left to right, iterating over elements using the marker I, whenever we hit greater than 18, we stop, or we go till we have not met this condition. And then after we have stopped here, then we do the same thing with J, for looking for the condition less than pivot value, right? Okay, if j is greater than I. That means the crossover has not happened. We have done the two whiles. If for any reason anyone has stopped anywhere, we have to check the condition. If j has not crossed over I, then what we do is array of I and array of j need to swap their values. Remember, we have to swap the values. If this particular thing is not familiar to you, what this does is something like this. If you have x and y, two variables, and you need to swap their values in Python, there is a very simple way of saying, okay, let me just say x and y are two elements, then x comma y is equal to y comma x, just swaps their values. Pretty nice, actually, pretty intuitive. I like this a lot. Instead of creating a temp variable and going through that in other cases, I really love this one. Okay, so this is where we are. And now, because we have swapped the values, we cannot stop till they have crossed each other, right? So we go with I plus equal to 1 and j, sorry, this is minus equal to 1, right? Now, after this, if it is, for example, if this condition is not met, then we have to break. Okay, once we have broken, that means here the crossover has happened, so we just have to break. Otherwise, it will just keep on going in that loop. Once the entire loop is over, once we have actually done looking at each of the iterable elements, then there is a final exchange. Remember this particular condition where I said the pivot element has to be exchanged with the element which is in its right position. So we have to do that. So here we say air of low, which is basically the pivot element, right? And which is the right position? J is the right position, because J would have traveled here to this position. J would have traveled, and it would have, if you remember here, J went till 13. Right, J went till 13, and then it crossed over at this point when it was at 6, isn't it? And now we are done. So this is a boundary condition. You might get confused with this, perhaps, that why am I using J? I suggest you use pen and paper to figure out why we are using J and I. Okay, because till it is, the condition says here J is greater than equal to I. Till that time I have to decrement J, and I had stopped at 13. J would have gone past. If you see here, I had stopped at 13, right? And then J started going back from 9, from 12, and went to 13, and then there was one more decrement which happened, and that is why it is at the right position. Okay, so now once we have got this, what we say is return J, because that's the correct position where we have to call low and correct position -1 and correct position +1 and high, right? So we return J. Now we have created the two partitions. We have also iterated over the elements in a way which we have seen in the example. Okay, now there is just one thing left to be done. All this sorting has to happen under a condition. The condition is if low is less than high. Because we are using low and high as the markers for the partition, not I and J, but the partition itself, there will come a time when they can cross over. For example, single element is remaining, we saw here, right? So 2 and 5, if you want to divide it into 2 and 5, then ultimately we'll be left with single element also. So they cannot cross over, otherwise they are pointing to the same element. So that condition has to be taken care of. right? And that really is all about this program. We also have to, so I have to test the program, and I am confusing between C and Python a bit too much. Okay, and what was the array? So we declare an array is 18, 7, 8, 13, 12, 9, 2, 5, 14, 6. Then we print the array so that we can see the actual array. We call Quicksort on the array, and finally we print it again. This should be the sorted array. Let us now run the program, and we see the 18, 7, 8, 13, 12, 9, 2, 5, 14, and 6. It comes out in the sorted fashion: 2, 5, 6, 7, 8, 9, 12, 13, 14, 8. What we will do now is also, we'll now work out a complete example. We went back and forth between the example and the program. We have written the complete program. We matched the program, the piece of the code with the logic behind the algorithm we were following. But now let us work out a complete program so that your understanding is complete. Here I've chosen a smaller example. 7 is the pivot element. So 8 is the ith marker and 5 is the jth marker. The condition here is greater than 7 and the condition here is less than 7. Is 8 greater than 7? Yes, it is. So we have to stop here. 5 less than 7? Yes, it is. So we have to stop here. And we have to interchange. So 5 comes here and 8 comes here. I then moves to 13. Is 13 greater than 7? Yes, it is. So we have to stop here. J points to 2 now. Is it smaller than 7? Yes, it is. So we have to stop here and we have to interchange these two. So 2 comes here and 13 comes here. Now I points to 12. Is 12 greater than 7? Yes, it is. So we have to stop here. J points to 9. Is it smaller than 7? No, it is not. So it moves forward. How about 12? 12 is greater than 7. But this is the point where I is pointing to. So the crossover has happened. So J is pointing to this. But remember, as per the code, we actually decrement it once more. So J now points to this location where currently 2 is. Okay. We write down 12 and 9 as such. And we have 7 here, but it has to be interchanged with the jth position. So these two are interchanged. So our new intermediate array is 2, 5, 7, 12, 9, 13, and 8. 7 is in the correct position. Now, there are two partitions, 2 and 5, and 12, 9, 13, and 8. For 2, this is the pivot element. So this is the ith element. This is also the jth element. And whatever you do, 2 is in the correct position. So 2 is written as this. Then you have 5, which will get written as this. 7 is in the right position. Now let's take 12. 12 is a pivot element. And so this is the ith element and this is the jth element. 9, is it greater than 12? It is not. 13, is it greater than 12? Yes, it is. So we have to stop at 13. We'll proceed with J. Is 8 less than 12? Yes, it is. So we have to stop here and we interchange this. So 8 comes here and 13 comes here. 9 is written as is, right? But where had J stopped? J had stopped over. So if we look at I, then I would go to 8. It has crossed over. So now 12 and 8 will be interchanged. So this will come as 8, 12, 9, 13, 7, 5, and 2. And out of these, 2, 7, and 12 are in their right positions. Then we look at 5. 5 is a single element, so it is in the right position. So nothing to be done here. Remember, this is the piece of the code where I had mentioned that we have to do the entire sorting only if low is less than high. So this falls in that branch. This falls out of that branch actually, and that is why nothing will happen here. 7. And now here 8 is a pivot element. So we have 8, we move, this is I element, and this is also the jth element, so 8 will just come here because 12 is already in the right position. So 9 is again a single element, 12 and 13, and this is a sorted array. Right, I hope the intuition behind this entire algorithm is clear to you. I have eaten up some steps here, but they were unnecessary repetitions. There's yet another variant to the implementation of this algorithm, wherein I marker is here and j marker is here, and 7th is the pivot element. So j goes from left to right looking for any value which is less than 7. So it goes till 2, and then it interchanges it with I plus 1. So I plus 1 position and j, they both swap. So 2 comes here, 13, 12, 9, 8 and 5. After that I is incremented, so I points here and j is pointing, j was pointing here, so j goes to 5, and 5 is again less than 7, so it increments, so it swaps the value with I plus 1, which is 13. So 5 comes here, 2 comes here, 12, 9, 8 and this is 13, and then finally 7 swaps the position with 5, so it becomes 5, 2, 7, 12, 9, 8, 13, and now 7 is in the correct position. 5 and 2, 12, 9, 8, 13 all are bigger than 7 are on the right side of it. This is also a very popular way. Both the conditions actually have their own caveats, so you should definitely check up on that. I think this is the approach that is implemented in CLRS. CLRS is for Corman's fantastic book on algorithm. So finally, some important points to note. This is a divide and conquer algorithm. Every time we choose a pivot and we put it in its right position, it divides the array into 2 partitions, and then we subsequently try to sort the 2 partitions in the same recursive way. So on an average, it takes n log n time, because every time we have put the element in the right position, we don't have to look at that element again, and we never have to compare elements on the left side to the right side. So that basically divides it into half, right? Yeah. The worst case scenario is O of n square happens when you have an already sorted input. This is not a stable algorithm. What it really means is that the input order of the data may not be preserved if they are equal on the keys. So if, for example, you have New York and David and New York and Macy, and that is the order in which they had appeared, in the final output, New York Macy can appear before New York David, right? So that is all about Quicksort. Please do like, share and subscribe this video. That helps motivate me to create more and better content. And I would also love to hear your thoughts and any feedback you might have on the video. Please do leave a comment. I hope to see you in the next algorithm topic. Thank you.